Right now, all around you, air is moving. Not wind exactly, nothing so dramatic as that, just the slow shifting of a fluid you happen to be sitting inside of, the way a fish sits inside water without ever really noticing the water. If a candle were burning nearby, its flame would lean and flicker with currents you can't see and probably can't feel. Currents caused by nothing more than a slightly warm wall, or the heat rising off your own skin, or a door closed somewhere down the hall an hour ago. Air is restless like that. It never really stops moving. And even though you think of the room around you as empty space, as nothing, it is actually made of trillions upon trillions of tiny particles, colliding with each other constantly, bouncing off your skin, right now, in numbers too large to picture, pressing against you from every direction at once, with a weight you've simply stopped noticing because you've never known anything else. This is worth sitting with for a moment, because it's easy to forget. The air in this room has mass. It has weight. If you could somehow gather up all the air in an average bedroom and pile it onto a scale, it would weigh something like the weight of a large dog, sitting invisibly in the corner, made of nothing you can hold in your hand. And this same ordinary substance, this air that fills your lungs without asking and drifts around candle flames and presses on your skin with a pressure you've never had to think about, this is the very thing that somewhere above the clouds tonight is holding up a machine that can weigh as much as 400,000 pounds, carrying several hundred people, their luggage, their coffee cups, their sleeping children, at a height where the air itself is thin and cold enough to kill you in minutes without help. It's a strange thought, if you let it sit there, the same fluid drifting lazily around your ankles right now, so gentle you'd never call it anything but calm air, is also, under the right conditions, capable of holding up something the size of a building, not by magic, not by some separate and mysterious force reserved just for flight, by the same physics that moves your candle flame, just organized, shaped, and set into motion in a particular way. For a long time, people found this contradiction almost impossible to accept, and honestly, it's not hard to understand why. Human beings evolved on the ground. We know, in our bones, what heavy things do. They fall. A dropped stone falls. A dropped apple falls. Anything with real weight, anything substantial, obeys gravity in a way that feels absolute, feels like a law, with no exceptions, because for nearly the entire span of human history, it was. There were birds, of course, and birds seemed to break the rule effortlessly, but birds were light, hollow-boned, feathered, clearly built for a different category of existence. A machine, made of metal, carrying dozens of adult humans, seemed to belong to gravity's side of the ledger, no matter what. And yet, tonight, at this very hour, there are airplanes crossing oceans, holding altitude as steadily as a table holds a cup of tea, and the air beneath their wings is not fighting some special exception to physics. It's the same air, the same molecules, behaving the same way they always behave, just meeting a very particular shape, moving through them in a very particular manner. This is really the heart of the whole puzzle, and it's worth letting it settle slowly before we go any further tonight. We are used to thinking of heavy and floating as two separate categories, opposites, things that don't mix. A leaf floats because it's light. A stone sinks or falls because it's heavy. But an airplane is heavy, genuinely, unmistakably heavy, heavier than almost anything else humans regularly put into motion, and it flies anyway,
not despite the ordinary rules of physics, but because of them, applied with extraordinary precision to something moving very fast, through something we usually dismiss as nothing at all. There's a comforting kind of order underneath all of this, once you start to see it, and that order is really what this whole story is about. It isn't about defying gravity. Nothing defies gravity. Gravity is still pulling down on that airplane above the clouds, with exactly the same insistence it pulls on you lying in bed right now. What's happening instead is a kind of quiet negotiation, a balance struck between gravity pulling down and something else pushing up, moment by moment, continuously, for as long as the aircraft is in motion. The forces don't cancel out because flight is effortless. They cancel out because they are being actively, constantly managed, the way a person riding a bicycle isn't magically immune to falling over, but is instead making 1,000 tiny unconscious corrections every minute to stay upright. Historically, this is roughly where curiosity about flight always seemed to stall out. People watched birds for centuries, sketched their wings, studied the angle of a soaring hawk, and still could not quite translate what they saw into something a human-built object could do. Leonardo da Vinci filled notebooks with drawings of wings and flying machines in the late 1400s and early 1500s, fascinated by birds in flight, convinced there had to be a mechanical answer hiding somewhere in their anatomy. He was right that the answer was mechanical. He simply didn't yet have the science of air itself, the understanding of pressure and flow that wouldn't really begin to take shape for centuries after his death. It's a gentle reminder that being observant isn't always the same as having the right framework to explain what you're observing. The framework, when it finally did arrive, came not from watching birds more closely, but from a completely different direction, from mathematicians and philosophers who became curious about fluids in general, water as much as air, how liquids move through pipes, how they speed up and slow down, how pressure changes as flow changes. It's an odd origin story for something that ends with a 400,000-pound machine crossing the Atlantic, but that's often how understanding arrives, sideways, from people asking questions that don't seem related at first. What all of this eventually revealed is something almost embarrassingly simple to state, even though the details take a while to unpack. Air moving in a particular way past a particular shape creates a difference in pressure. Higher pressure in one place, lower pressure in another. And whenever there's a difference in pressure like that, nature doesn't tolerate it quietly. Something has to happen. In this case, what happens is a net push, a force in the direction from high pressure toward low pressure, strong enough, if the shape and the speed are right, to lift an enormous weight right off the ground and hold it there. That's really all lift is, at its core, before we get into any of the specifics. A pressure difference, created by moving air, resolving itself into an upward push. It sounds almost too plain to explain something as improbable looking as a jumbo jet cruising along at altitude, wings barely flexing, engines humming steadily, seeming to simply sit in the sky as though the sky were solid ground. But improbable looking and physically impossible are two very different things. And tonight, slowly, without any rush at all, we're going to walk through exactly how that plainness becomes something powerful enough to carry hundreds of sleeping strangers 35,000 feet above the ocean, held up the whole time by nothing more than air. Before we get to wings themselves, though, and the particular shapes engineers eventually settled on, it helps to slow down even further and get comfortable with air as a substance in its own right. Not air as an idea, or air as empty space, But air is something with texture, something with rules, something that behaves in ways that are actually fairly intuitive once you've watched it closely enough. Because to understand how a wing lifts a plane, you first have to understand what it even means for something invisible to push, to flow, to speed up and slow down, to have a kind of personality of its own as it moves. And that's where we'll go next, gently, starting with the simple truth that air, despite seeming like nothing, is really something.
Let's start with something small. Imagine standing in a quiet room, no fans running, no windows open, nothing moving that you can see. It feels empty. It feels like there's nothing between you and the far wall except distance. But that's not true, and it's worth sitting with how untrue it is, because the whole story of flight depends on taking air seriously as a physical thing rather than an absence. That room is filled, every corner of it, with molecules of nitrogen and oxygen and small amounts of other gases, moving in every direction at once, colliding with each other and with the walls and with you, constantly, at speeds that would sound absurd if you weren't already used to ignoring them. At room temperature, the average air molecule is moving at somewhere around 1,000 miles an hour, not drifting, not floating gently like a feather, careening, and then, almost immediately, it collides with another molecule and bounces off in some new direction, and that happens again and again, billions of times a second, in every cubic inch of that quiet room you thought was still. So when we say air is invisible, what we really mean is that it's made of particles too small and too numerous for our eyes to resolve individually. But invisible doesn't mean absent, and it certainly doesn't mean weightless in the way we sometimes carelessly use that word. Air has mass. A cubic meter of air at sea level weighs a little over a kilogram, roughly the weight of a liter bottle of water. Multiply that by the volume of a room, or a stadium, or the sky above a city, and you start to get a sense of just how much stuff is up there, pressing on things, being pressed on in turn. This is a good moment to introduce a word that will come up again and again tonight, and it's worth getting comfortable with now, unhurried. Density. Density is simply how much mass is packed into a given space. A brick and a sponge can be the same size and yet feel completely different in your hand because the brick has far more mass squeezed into that volume. Air has a density too, and it's not fixed. It changes with temperature, with altitude, with how tightly the molecules happen to be crowded together at any given moment. Air near sea level is denser than air at the top of a mountain because there's more atmosphere stacked above sea level, pressing down and compressing the layers below it. This is part of why people get short of breath climbing a tall peak. Each breath at altitude simply contains fewer molecules of oxygen because the air itself is thinner, less densely packed. Density matters enormously for flight, and we'll return to it later when we talk about why airplanes fly best at certain altitudes and why the air feels different to an engine at 30,000 feet than at sea level. But for now, just let the idea settle. Air is matter. It has weight. It can be dense or thin. It is not nothing. Now, alongside density, there's pressure, and it's easy to blur these two ideas together, so it helps to separate them clearly, slowly, the way you might sort two kinds of buttons into two different jars. Pressure isn't about how much air there is in a space. Pressure is about how hard that air is pushing,
in every direction, on whatever it happens to be touching. Picture those molecules again, careening around at hundreds of miles an hour, bouncing off every surface they meet. Each individual collision is a tiny, almost immeasurable tap.
But there are so many of these taps happening every second, on every square inch of every surface, that added together, they produce something you can actually feel and measure, a steady, continuous force, pushing outward in all directions at once. This is why a balloon holds its round shape. The air inside is being struck by countless molecular collisions on the inside of the rubber, pushing outward evenly, while the air outside is pushing back in, also evenly, and the rubber sits in a kind of quiet standoff between the two. This is also why, if you've ever felt your ears pop on an airplane during takeoff or descent, you felt pressure directly and personally. The air pressure outside your body was changing as the plane climbed or descended, while the air trapped in the small spaces behind your eardrums adjusted more slowly, and for a moment there was an imbalance, a difference between inside and outside, and your body noticed. That word, difference, is going to matter more than almost any other word in this entire story, so let it settle in gently. Pressure by itself, sitting quietly and evenly around an object, does nothing dramatic. It's balanced. It's the kind of thing you stop noticing, the way you stop noticing the hum of a refrigerator after the first few minutes in a room. But pressure that's higher on one side of something than another, even by a tiny amount, creates an imbalance that the air itself seems eager to correct. And when that correction happens across the surface of something shaped just right, moving through the air just right, that correction becomes a force, a push. And under the right conditions, that push becomes lift. We'll get to the exact shape of a wing soon, and to the reasons the air ends up faster in one place than another around it. But there's another property of air worth sitting with first, one that people often overlook entirely, and it's viscosity. Viscosity is a word usually reserved for liquids. You've felt it. If you've ever poured honey compared to pouring water, honey resists flowing. It clings to the sides of the jar, drags against itself, moves reluctantly. Water, by comparison, flows almost carelessly, slipping past itself with very little internal resistance. That reluctance, that internal friction within a fluid, is viscosity, and air has it too, even though we rarely think of air as sticky or draggy in any way. Air's viscosity is far lower than honey's, obviously, lower even than water's, but it is not zero. As air flows across a solid surface, like the metal skin of a wing, the very thinnest layer of air molecules right against that surface tends to slow down, almost sticking to it, clinging, just slightly, the way dust clings to a fan blade, even while the blade is spinning through open air. That thin, slowed layer drags gently on the layer just above it, which drags a little less on the layer above that, and so on, until a few inches or feet away from the surface, the air is moving at its full, undisturbed speed again. This gradually shifting zone has a name, the boundary layer, and it turns out to be quietly important to how wings actually behave, something we'll come back to later in the night when we talk about turbulence and why wings sometimes stop working properly at certain angles. For now, the point is simply this: air is not a perfectly smooth, frictionless, idealized substance.
It drags on itself a little. It has texture, a kind of subtle internal stickiness, and that stickiness has real consequences for anything moving through it. There's one more idea worth laying down carefully before we move toward wings themselves, and it's the relationship between speed and force, something physicists call momentum. Momentum is simply the product of how much mass something has and how fast it's moving. A bowling ball rolling slowly down a lane carries a certain amount of momentum. Speed it up and that momentum increases. Air, being made of countless tiny masses in motion, carries momentum too, in whatever direction it happens to be flowing. And here's the part that will matter greatly once we reach the wing itself. When you change the direction that air is moving in, or change its speed, you are changing its momentum, and changing momentum requires a force, and forces come in pairs. If a wing pushes air downward, the air pushes back upward on the wing with exactly the same strength. This isn't a metaphor or a rough approximation. It's one of the oldest and most reliable relationships in all of physics, and it will turn out to be just as central to understanding lift as the pressure story we started with.
So here is where that leaves us, resting for a moment before we go further. Air is made of real particles, in constant frantic motion, colliding trillions of times a second. It has density, meaning it carries real mass through real space. It has pressure, meaning those countless collisions add up to a steady outward push, one that becomes powerfully important the moment it's unequal from one place to another. It has viscosity, a faint internal stickiness that shapes how it clings to and slides across solid surfaces. And it carries momentum, the simple product of mass and motion, which means that pushing air one way always means being pushed back the other. With all of that quietly in place, we're finally ready to bring a wing into the picture, and to ask, slowly and carefully, what actually happens to the air the moment it meets one. Picture a wing lying on a workbench, not yet attached to anything, not yet moving through anything, just sitting there so you can look at its shape without the distraction of speed or sky. If you sliced straight through it, from the rounded front to the thin back, and looked at that slice from the side, you'd be looking at what engineers call an airfoil. This cross-sectional shape is really the whole story of the wing, repeated over and over along its length, and it's worth spending a quiet moment getting to know its geography. The front of this shape, the part that meets the air first, is called the leading edge, and it's usually gently rounded, almost like the curve of a spoon. The back of the shape, where the wing tapers away to almost nothing, is called the trailing edge, and it's typically thin, sometimes thin enough to nearly disappear into a line. If you draw a straight line, connecting the leading edge to the trailing edge, from the very front point to the very back point, that imaginary line has a name too. It's called the chord line, and it functions like a kind of ruler laid across the wing's shape, a reference against which everything else can be measured. The chord line doesn't follow the curves of the wing. It just connects the two endpoints directly, the way a tightly pulled string would if you stretched it from the front tip to the back tip and let everything else fall away. Now, here's something that surprises a lot of people the first time they really look closely at a wing's cross-section. The wing itself is almost never shaped like that straight chord line. Instead, the upper surface curves upward and then sweeps back down, while the lower surface often stays flatter or curves much more gently, sometimes barely curving at all. This asymmetry, this gentle bulge of the upper surface relative to the chord line, is called camber. You can think of camber as a kind of quiet, deliberate imperfection, a way of saying that if you compare the actual curved shape of the wing's top surface to that straight imaginary chord line beneath it, there's a gap, a rise, a little hill of extra material sitting above where a flat surface would be. Some wings have a lot of camber, with a pronounced curve on top. Others have very little, closer to a symmetrical shape, where the top and bottom mirror each other almost exactly. Both kinds of wings can produce lift, which is a detail we'll return to later, because it turns out camber alone doesn't explain everything, no matter how often it gets credited with doing so. Beyond the shape itself, there's the question of orientation, of how this shape is tilted relative to the air flowing past it. And this is where we meet a concept called angle of attack. Angle of attack is simply the angle between that chord line we just described and the direction the oncoming air is traveling. If the wing is angled so that its leading edge points slightly upward relative to the airflow, the angle of attack is positive, and the whole wing is tilted a bit like the way you might tilt your flattened hand out of a car window, catching the wind at a slight upward slant rather than holding it perfectly level. If the wing is angled the other way, with the leading edge tipped down relative to the airflow, the angle of attack is negative, and if the chord line points exactly along the direction the air is moving, with no tilt at all, the angle of attack is 0. It's worth sitting with the difference between camber and angle of attack for a moment, because they're easy to blend together in your mind, even though they're really quite separate ideas. Camber is a property of the wing's shape itself, built into the metal or composite material, fixed once the wing is manufactured, the same whether the plane is parked on the tarmac or cruising at altitude. Angle of attack, on the other hand, isn't a property of the shape at all. It's a property of the relationship between the wing and the air moving past it, and it changes constantly during flight, adjusted by the pilot tilting the aircraft's nose up or down, changing moment to moment as the plane climbs, descends, turns, or simply shifts in a gust of wind. A wing keeps its camber wherever it goes. Its angle of attack is more like a mood, something that shifts with circumstance. Now let's bring air back into the picture. Air that we spent the earlier part of this narration getting to know so carefully. Air with its mass, and its pressure, and its faint internal stickiness. Imagine this air approaching the wing from ahead, flowing steadily toward that rounded leading edge. Because of viscosity, that faint clinginess we talked about, the air doesn't just glance off the wing's surface and bounce away. Instead, a thin layer of it, called the boundary layer, actually follows the contour of the wing quite closely, hugging the curve of the upper surface and tracing the shape of the lower surface too. The way a stream of water poured slowly over a rounded stone will often follow the stone's curve rather than shooting straight past it. As the air divides at the leading edge, some of it travels over the top of the wing and some travels beneath, and because of the wing's shape and its angle of attack together, the air moving over the top is forced to curve, to bend along a path that isn't straight anymore. This bending is important, because remember, we established earlier that changing the direction of moving air requires a force, and that force always comes paired with an equal and opposite reaction. The wing is pushing on the air, nudging it into a curved path, instead of letting it continue straight ahead, the way it would in perfectly undisturbed space, and the air, in turn, is pushing back on the wing. At the same time, something else is happening to the air as it flows over that curved upper surface, something involving speed and pressure together. Because the air is following the contour of the wing, and the contour of the wing curves away beneath it, the air over the top tends to move through a path that effectively asks more of it, geometrically, than the flatter path underneath. Exactly how this connects to speed and pressure has been explained in different ways by different people over the decades, and not all of those explanations have aged equally well. Something we'll examine slowly and honestly a little further along in this narration. But what can be said carefully, without overreaching, is that pressure across the wing's surface doesn't stay uniform. Above the wing, the air tends to be at lower pressure. Below the wing, it tends to be at higher pressure. And whenever you have higher pressure pushing up from below and lower pressure pushing down from above, meeting at the same surface, the surface feels a net push in the direction of the lower pressure. In this case, that means an upward push on the wing. This is sometimes called circulation, a slightly technical word for the pattern of airflow that develops around a wing once it's producing lift, where the air moving over the top tends to be sped up and the air underneath tends to be slowed down relative to what it would be doing if the wing weren't there at all, creating a kind of net swirl in the flow pattern surrounding the shape, even though no actual water wheel spinning is occurring. It's a mathematical description as much as a physical one, a way of characterizing the overall pattern rather than pointing to any single visible motion, but it turns out to be a genuinely useful concept, one that shows up again and again in the more careful accounts of how lift actually works. So notice that we now have two descriptions running alongside each other, not competing so much as describing the same event from different vantage points. There's the Newtonian description, the one about momentum, where the wing deflects air downward and the air pushes the wing upward in return, a direct consequence of that ancient and unshakable law about equal and opposite reactions. And there's the pressure description, the one about circulation and lower pressure above, higher pressure below, and a net upward push resulting from that imbalance. Both descriptions are talking about the same wing, the same air, the same lift. They aren't rival theories, where one must be right and the other wrong. They're more like two honest witnesses describing the same event from different angles, each one true, each one incomplete on its own, and each one made richer by the other. Before we go further into exactly how these two descriptions connect, and where some popular explanations of lift quietly go astray, it's worth pausing here, letting the shape of the wing settle in your mind, its curve, its tilt, the air dividing gently at its leading edge and reuniting somewhere behind its trailing edge, before we turn to the question of what actually happens to air molecules that take the longer path over the top. Let's stay with that image for a moment, air dividing at the leading edge, and follow one particular piece of folklore that has been told to generations of curious passengers, usually somewhere around cruising altitude, usually by someone who genuinely believes they're helping. The story goes like this. A wing is curved more on top than on the bottom. A parcel of air arrives at the leading edge and splits into two, one half going over, one half going under. Because the trip over the top is longer, that upper parcel has to move faster to cover the extra distance. And here's the part that makes the whole story hang together, or seems to. The two halves are supposed to meet up again at the trailing edge, arriving at exactly the same moment, like two hikers who took different trails around a hill and agreed in advance to meet at the bottom at noon. Faster air over the top, the story continues, means lower pressure over the top by Bernoulli's principle, and lower pressure on top means lift. It's tidy. It's easy to draw on a napkin. It has been printed in flight training manuals, museum placards, and children's encyclopedias for the better part of a century. And it is not correct, at least not in the way it's usually told. and the reason it's not correct is worth sitting with slowly, because untangling it teaches you something true about both Bernoulli's principle and about how air actually behaves. Start with the meeting up claim, the idea that the two divided parcels reunite at the trailing edge at the same instant. There is no law of physics that requires this. Nothing in fluid dynamics obligates two adjacent bits of air to stay in sync just because they happen to separate at the same point. If you've ever watched a stream split around a rock, you may have noticed the two braids of water don't necessarily rejoin in perfect unison downstream. Sometimes one side is visibly ahead of the other, swirling past while its former neighbor is still working its way around. Air over a wing behaves in an analogous way, and researchers who have used smoke visualization in wind tunnels, releasing thin streams of smoke upstream of a wing and watching how they deform as they pass over and under it, have shown this rather beautifully. The air that goes over the top does not patiently wait for its counterpart below to catch up. It arrives at the trailing edge well ahead of schedule, sometimes considerably so. The equal transit time story isn't just an oversimplification, it's describing an event that doesn't actually happen. So then why does the air over the top move faster at all, if not because it's racing to keep an appointment at the back of the wing? This is where it helps to slow down and think about what's actually causing air to speed up or slow down in the first place, which is pressure difference, not geometry alone, and certainly not any obligation to arrive somewhere on time. Once a wing is producing lift, the pressure above it is lower than the pressure below it, for reasons connected to that circulation pattern we were just describing, the net swirl in the flow around the wing's shape. And once you have that pressure difference established, the air responds to it the way fluids always respond to pressure differences, by accelerating from high pressure toward low pressure. The air over the top isn't fast because it's covering extra distance and needs to hustle. It's fast because the pressure field around the wing is pushing it that way. The curvature of the upper surface matters, but it matters because of how it shapes that pressure field, not because it imposes a race with a fixed finish time. This is a good moment to be honest about something that trips a lot of people up, which is what Bernoulli's principle actually claims, because the equal transit time story borrows Bernoulli's name while getting the relationship slightly backwards in how it's usually explained. Bernoulli's principle, worked out by Daniel Bernoulli, a member of a rather extraordinary Swiss family that produced mathematicians the way some families produce lawyers or doctors, describes a relationship between pressure and speed along a streamline in a moving fluid. Where the fluid speeds up, pressure drops. Where it slows down, pressure rises. This falls out of the conservation of energy. Essentially, the fluid trading one form of energy associated with pressure for another associated with motion as it moves along its path. It's a real principle, thoroughly tested and genuinely relevant to what happens around a wing. But notice the direction of causation implied by the popular story versus what's actually happening. The napkin version says, the air is fast because it has far to go, and therefore the pressure is low. But the more careful account says the pressure is low because of the overall flow pattern the wing establishes, that circulation we talked about, and the air is fast as a consequence of that lower pressure, not the cause of it. Speed and pressure are locked together. Yes, exactly as Bernoulli described, but neither one is straightforwardly the cause of the other
in some simple one-directional sense. They rise and fall together, in the same way that the height of water on either end of a seesaw rises and falls together, without either end causing the other in a way you could point to and call fundamental.
What actually sets up the whole pattern?
What determines that there will be a pressure difference at all involves the wing's angle, its shape, and the way it interacts with the surrounding air to establish that circulation, which then expresses itself simultaneously as both a speed difference and a pressure difference, two faces of the same underlying flow. There's a smaller error worth mentioning too, tucked inside the equal transit time story, which is the assumption that the upper surface being longer automatically means it takes more time to traverse, if speed were equal. That's true only if you assume the speeds are what you're trying to derive, which is circular reasoning dressed up in convincing clothing. It sounds like an explanation. It even sounds like it's using real physics, since Bernoulli's name is right there in the next sentence. But if you follow the logic closely, it quietly assumes its own conclusion, and once that assumption is removed, the tidy little rendezvous at the trailing edge falls apart entirely. None of this means Bernoulli's principle is wrong or unhelpful, and it would be a mistake to let this correction curdle into the opposite myth, the one where people swing too far and start insisting Bernoulli has nothing to do with lift at all, that it's some kind of debunked footnote and only Newton's laws are the real story. That's an overcorrection, and you'll sometimes find it in places that pride themselves on myth-busting, and it trades one oversimplification for another. Bernoulli's principle is doing real work here. It correctly describes the relationship between the speed and pressure fields once you understand the actual pattern of circulation that develops around a lifting wing, the pattern we described a little earlier as air sped up on top and slowed down below relative to the undisturbed flow. What's wrong isn't Bernoulli's principle itself, it's the specific, oversimplified story about equal transit times that gets bolted onto it, a story that was never really Bernoulli's claim to begin with, more of a folk addition that grew up around the real physics like ivy around a fence post, obscuring the structure underneath while looking, at a glance, like it belongs there. So where does that leave us, with the air over the top arriving early? It arrives early because the pressure field, established by the overall circulation around the wing, accelerates it forward, the same way water speeds up when squeezed through a narrower channel, or the way traffic speeds up on a highway once it merges from a wide multi-lane road into fewer lanes moving fast, a pressure difference doing its ordinary, unmysterious work. There's no appointment being kept, no rule requiring symmetry between the parcels above and below, nothing magical or teleological about it at all. Just a fluid responding, moment by moment, to the pressure differences the wing's shape and angle have set up around it, in a pattern that happens to run a little ahead of schedule on top and a little behind on the bottom, with no clock forcing them back into step. And once you set aside the idea of parcels needing to reunite, a new and more interesting question opens up, one about where that circulation pattern actually comes from in the first place, what starts it, and why a flat, symmetrical surface can sometimes produce nothing like it at all, while the slightest tilt changes everything.
Let's leave that question resting quietly for a moment, the way you might leave a book open on a table, spine cracked to the page you'll return to, and walk instead onto the airport tarmac itself, where all this theory has to actually go to work. Picture the airplane sitting at the gate, engines idling, nothing more dramatic happening then the low hum you might not even notice unless you were listening for it. At this moment, lift is not a factor in anyone's thinking. The wings are just wings, shaped the way we described, ready but idle, like a violin resting in its case. What matters here is weight, and only weight, pressing the tires down against the pavement, the whole mass of the aircraft, fuel and passengers and luggage, and the airframe itself, held up entirely by the ordinary mechanical strength of rubber and steel and concrete, the same principle that holds up a parked car or a loaded shopping cart. Nothing aeronautical about it yet at all. Pushback begins, and the plane is nudged backward by a small tug, because most aircraft cannot easily reverse under their own power, and then the engines spool up gently, and the plane begins to taxi, rolling along at a pace not much faster than a brisk walk, weaving along yellow lines painted on the ground the way a car follows lane markings on a highway. During taxi, the wings are doing essentially nothing aerodynamically interesting. The airspeed is too low, and airspeed, remember, is the whole currency this system runs on. Lift depends on the square of airspeed, which means if you double how fast air moves across a wing, you don't get twice the lift, you get 4 times the lift, and if you halve the speed, you don't lose half the lift, you lose 3/4 of it. This squared relationship is one of the quiet reasons everything about takeoff has to happen the way it does, in a fairly narrow, carefully calculated speed range, because lift doesn't scale gently, it scales steeply, like compound interest, small changes near the low end producing very little, and small changes near the necessary threshold producing a great deal all at once. So the airplane taxis to the runway, and here it typically pauses, lined up with the long strip of pavement ahead, engines idling again for just a moment, the pilots running through final checks, flaps set to a specific position that we'll come back to in a moment, because flaps matter enormously here, and almost not at all a few minutes from now. Then the pilot advances the throttles, and the engines, whether jet turbines or propellers, begin producing thrust, which is simply the forward push generated by accelerating air or exhaust gases backward, the same reaction you feel if you've ever stood behind a large fan or let air out of a balloon and watched it zip across a room, force pushing one way, the object shooting the other way, Newton's third law doing its patient, reliable work. The airplane begins to roll forward, and at first, this feels like nothing more than a very smooth car ride, faster and faster, the runway markings blurring past the windows, engine noise climbing steadily. What's actually happening, underneath that ordinary sensation, is that airspeed is climbing too, and with it, according to that squared relationship, the amount of lift the wings are capable of generating is climbing far faster than the speed itself. At 40 miles an hour, the wings are producing only a trickle of lift, nowhere near enough to matter. At 80, they're producing 4 times that trickle. At 160, 16 times as much. The airplane isn't accumulating lift steadily, the way you'd fill a glass with water at a constant rate. It's more like the lift is compounding, gathering itself slowly and then suddenly, the way a rolling snowball picks up mass faster and faster as its surface area increases. Though the physics here is different, the metaphor is just meant to capture that sense of quiet, then rapid, then quiet, then rapid growth. While all this is happening, flaps and slats are already doing something important, and they've likely been doing it since before the airplane even left the gate. Flaps are hinged panels along the trailing edge of the wing, the back edge, and slats are similar panels along the leading edge, the front edge, and both of them, when extended, change the effective shape of the wing rather dramatically. Think of the wing's ordinary shape as a smooth, unremarkable file folder, gently curved.
Extending flaps is a bit like opening that folder wider at the back and adding a curved flap of extra material, increasing the wing's camber, its curvature, and often increasing its total surface area as well.
This does two useful things at once. It increases how much lift the wing produces at any given speed, and it also increases drag, the resistance pushing back against forward motion, which sounds like an unwelcome trade, until you realize why it's exactly what's wanted at this particular moment. During takeoff, the goal is to generate enough lift to leave the ground at the lowest possible speed that's still safe, because runways, however long they look from a passenger's window seat, are a finite resource, and using less of one is generally preferable to using more. By deploying flaps and slats, the wing becomes, in effect, a more efficient lift generator at low speed, willing to produce the needed lift even before the airplane has built up the kind of velocity it would need with the wings in their clean, retracted configuration. It's a bit like the difference between trying to catch a beach ball with your bare hands versus catching it in a wide net, the net doing more of the work at lower effort, gathering more from less. The trade-off is that this configuration creates more aerodynamic drag, more resistance, which is one reason flaps aren't left extended once the airplane is cruising along at high altitude, where efficiency, not maximum lift at minimum speed, becomes the priority. As the airplane continues accelerating down the runway, the pilots are watching for a specific number, a speed calculated in advance, based on the aircraft's weight, the day's temperature, the elevation of the airport, and a handful of other variables, a number often called rotation speed. This is the point at which the wings, given their current shape, their current angle, relative to the airflow, and the current airspeed, are finally producing enough lift to support the aircraft's full weight, or very nearly enough, with a bit more expected, the moment the nose comes up. When that speed arrives, the pilot gently pulls back on the controls, and the nose of the airplane lifts, not because pulling upward on a control column physically yanks the airplane into the sky, but because that motion increases the wing's angle of attack, the tilt we discussed earlier, which increases the lift coefficient, which increases lift itself, all in that same smooth continuum where higher tilt has meant higher lift. This moment, called rotation, is the hinge point of the entire takeoff, the instant weight and lift, which have been in a private, invisible contest since the throttles first advanced, finally tip in lift's favor. Weight hasn't gone anywhere, it's still there, pulling down exactly as hard as it did while the plane sat at the gate. What's changed is that lift has grown to match it, and then slightly exceed it, and in that narrow window, the airplane rises off the runway, tires leaving pavement, often so gently that passengers only realize it's happened because the rumbling stops and the ride, all at once, goes quiet and smooth. There's a subtlety worth sitting with here, something pilots learn to feel almost instinctively, but that's easy to overlook from a passenger's seat. In the first few dozen feet after leaving the ground, the airplane is flying through what's called ground effect, a zone of altered aerodynamics that exists only very close to the surface, roughly within one wingspan of height. Down here, the ground interferes with the way air would otherwise flow off the wingtips and trailing edge, reducing a certain kind of drag, called induced drag, and effectively making the wing a little more efficient than it will be once it climbs higher. It's a bit like the difference between swimming close to a pool wall, where the water seems to push back and help you along a little, versus swimming out in open water, where that boundary support disappears. Pilots sometimes feel this as the airplane wanting to float just above the runway rather than climbing away crisply, and part of the skill of flying involves accounting for that temporary boost. not mistaking it for more performance than the airplane will have a few seconds later, once it's climbed clear of the ground's influence and the ordinary rules resume. Once truly airborne and climbing, the landing gear retracts, folding up and out of the airflow, because a lowered wheel, dangling in the wind, does nothing but add drag when it's no longer touching pavement, the aviation equivalent of tucking in loose shoelaces before a run. The flaps, too, will be gradually retracted as the airplane gains speed, drawn back in stages rather than all at once, because at higher speed, the wing no longer needs that exaggerated curvature to produce sufficient lift, and keeping the flaps out longer than necessary would simply mean dragging around extra resistance for no benefit, spending fuel and efficiency on a shape the airplane has already outgrown. And so the airplane climbs, angle of attack, airspeed, wing shape, and thrust, all still cooperating, still balancing weight, but now with room to breathe, altitude opening up beneath it, the runway shrinking behind, and a whole new set of questions waiting quietly overhead about what changes and what doesn't, as the air itself grows thinner, the higher the airplane goes. Eventually, the climb ends, not with any dramatic gesture, but with a kind of quiet settling, the nose easing down a degree or two, the engines easing back from their climb power, and the airplane leveling into what pilots simply call cruise. This is the part of the flight most passengers sleep through, and there's a reason for that, beyond simple boredom. Cruise is, by design, the calmest regime an airplane ever occupies. Almost everything that was changing during takeoff and climb has now stopped changing, and stillness, once you understand why it's happening, turns out to be one of the more remarkable parts of the whole flight. Think back to that idea of forces in balance, weight pulling down, lift pushing up, thrust pulling forward, drag pulling back. During takeoff and climb, these were not equal. Thrust was deliberately set higher than drag, so the airplane could accelerate and gain altitude, and lift was arranged to slightly exceed the pull of gravity, so the airplane could rise. Climbing is, in this sense, a controlled imbalance, a small and continuous overpowering of the forces that would otherwise hold the airplane down or still. Cruise is the opposite. Once the airplane reaches its assigned altitude, the pilots, or more often the autopilot, ease the nose to a level attitude and adjust engine power until the four forces settle into something close to equilibrium. Lift equals weight. Thrust equals drag. Nothing is winning, nothing is losing, and an airplane in that condition has no reason to climb, descend, speed up, or slow down. It simply continues, more or less in a straight line, at more or less a constant altitude, for as long as that balance holds. There's something worth sitting with in that word equilibrium, because it explains a lot about why cruising flight feels the way it does. A rock resting on a table is in equilibrium too, gravity pulling it down, the table pushing back up with equal and opposite force, and the rock, understandably, does not do anything. It just sits there. An airplane in cruise is a stranger cousin of that same idea, a rock that happens to be moving forward at 500 miles an hour while still being, in every vertical sense, at rest. The forces holding it at altitude are just as balanced as the forces holding that rock on the table, even though the airplane itself is anything but stationary. This is part of why the sensation of speed disappears at cruising altitude. Down near the ground, your body reads velocity by watching things rush past close to you, a fence post, a road sign, a passing car. At 35,000 feet,
The ground is so far below, and the clouds so far to the side, that nothing nearby is rushing past at all, and your inner ear, which senses acceleration and changes in motion far better than it senses constant motion itself, has nothing to report. Constant velocity, it turns out, feels exactly like sitting still, whether you're in an airplane, a smoothly gliding elevator, or, as Einstein once pointed out, in a slightly different context, drifting through space at any speed at all, so long as nothing is pushing or pulling unevenly on you. Of course, no balance in the real atmosphere is ever perfectly permanent, and this is where trim and small, continuous correction enter the story. Air is not a uniform, unchanging medium. It has texture, patches of slightly warmer or cooler temperature, faint currents, the occasional ripple of turbulence too gentle to notice as anything more than a light shimmer through the cabin. Fuel is also being burned continuously, which means the airplane is very slowly getting lighter over the course of a long flight, sometimes by tens of thousands of pounds between departure and arrival, and a lighter airplane needs very slightly less lift to stay level than a heavier one did an hour earlier. Left completely alone, these small influences would nudge the airplane's nose up or down by fractions of a degree, and over time, those fractions would add up to a real drift in altitude. This is where trim comes in, and it's worth understanding because it explains why pilots are not constantly wrestling with the controls hour after hour, the way a car commercial might suggest. Trim is, at its simplest, a way of adjusting the resting position of the control surfaces so the airplane holds a particular attitude on its own, without the pilot needing to apply constant pressure. Picture holding a car's steering wheel dead straight down a long, slightly cambered highway. If the road tilts just a little to one side, you'll find yourself applying a faint, constant pressure to keep the car from drifting, a pressure your arm will start to feel after enough miles. Now imagine a small wedge you could slide under one side of the wheel that held that same faint pressure for you, permanently, so your hands could rest lightly on the wheel and simply monitor, rather than labor. That's close to what trim does for an airplane's elevator, the small movable surface on the tail that governs whether the nose wants to rise or fall. Adjust the trim correctly, and the airplane will hold a level attitude with the control column essentially untouched, the aerodynamic forces on the tail balanced against gravity's effect on the airplane's nose without any ongoing muscular effort from the person flying it. Pilots trim the airplane, feel how it settles, then trim again as fuel burns off and conditions shift, small adjustments made every so often rather than one constant fight against imbalance.
Much of this work, on modern airliners, is handed to the autopilot, and it's worth pausing on what that machine is actually doing, since the name suggests something grander than the reality. An autopilot is not flying the airplane in any imaginative or decision-making sense. It is, at its heart, a system of sensors and small motors carrying out an extremely narrow and repetitive task, comparing the airplane's current altitude, heading, and speed against the values it's been told to hold, and making tiny, continuous corrections whenever it detects the smallest deviation. If the nose begins to creep up half a degree, the autopilot notices within a fraction of a second and applies a whisper of correction through the elevator before a human pilot would have had time to consciously register the change at all. It's less like a second pilot and more like an extremely attentive, extremely literal-minded assistant whose entire job is watching a handful of needles and nudging them back to where they belong, over and over, thousands of times an hour, tirelessly,
and without any interest in doing anything more ambitious than that. The first rudimentary version of this idea appeared remarkably early, in 1912, built by Lawrence Sperry, the son of the gyroscope pioneer Elmer Sperry, who famously demonstrated his invention at a flying exhibition near Paris by standing up in the cockpit with his hands raised while the airplane flew itself, a piece of showmanship that also happened to be a completely genuine proof that machines could hold an airplane steady without continuous human input.
This brings us to a detail that surprises a lot of people once they hear it clearly stated, which is that the engines, in cruise, are not really working to hold the airplane up at all. Lift is doing that job, generated by the wing moving through the air, exactly as it was during climb, just now, in a quieter, more settled form. What the engines are mostly doing in cruise is a narrower task, simply overcoming drag, the resistance the air offers to anything moving through it. Since thrust and drag are balanced in cruise, and drag at a steady altitude and speed tends to be relatively modest compared to what's needed for climbing, engines at cruise power are often running at a noticeably lower setting than they were just minutes earlier, fighting a smaller battle now that the airplane isn't also trying to gain height. If every engine on an airliner failed simultaneously at cruising altitude, and this is a scenario pilots train for specifically, the airplane would not fall out of the sky like a dropped stone. It would glide, descending slowly, trading altitude for forward speed, the wings still generating lift the entire way down, sometimes for well over 100 miles depending on the altitude and aircraft type, which is part of why several well-known cases of complete engine failure at cruise, including flights that lost power over open ocean or after encountering volcanic ash, ended with the airplane reaching a runway rather than the ground reaching it first. All of which helps explain why cruising flight so often feels less like traveling and more like simply existing somewhere very high and very still, an equilibrium of forces so quiet it barely announces itself, disturbed only occasionally, and only briefly, by an unseen texture in the air, far above the ground. Since drag was the thing the engines were quietly fighting all along, it deserves a slower look, because drag is not one force but several, layered on top of each other, each with its own personality and its own place in the story of how an airplane moves through the sky. The simplest form to picture is skin friction drag, and you can feel a version of it yourself by holding your hand flat out of a car window at moderate speed, palm down, and noticing that even a perfectly smooth flat surface meets some resistance just from the air sliding across it. Air is not nothing. It has a faint stickiness to it, a viscosity, and as it flows across any surface, a very thin layer right next to that surface gets dragged along slightly, slowed down by friction with the material itself, the way water near a riverbank moves slower than water in the middle of the current. This thin, slowed layer is called the boundary layer, and its behavior turns out to matter enormously. Early in an aircraft's design history, engineers didn't fully appreciate how much of an airplane's total drag came from this seemingly trivial surface friction, because it feels like such a small thing compared to the dramatic business of generating lift. But skin friction adds up across the entire wetted surface of an airplane. Every rivet line, every panel seam, every square foot of fuselage and wing and tail, and for a large jet cruising efficiently, it can account for a significant share of the total drag the engines are working against. This is part of why modern airliners are polished and smoothed with such obsessive care, why paint is applied thinly and evenly, why panel gaps are minimized, why even small surface imperfections get attention during manufacturing that might seem excessive for something that large and heavy. A rough surface disturbs that thin boundary layer, making it turbulent instead of smooth, and turbulent boundary layers create more friction drag than smooth ones, so smoothness genuinely saves fuel over the life of an airplane, not just in a marketing sense, but in a measurable one. Then there is pressure drag, sometimes called form drag, which has a different character altogether. This is the drag that comes from an object's overall shape, from how air has to part around it at the front and then rejoin behind it. Picture pushing a flatboard through water, edge first, then broadside, and you'll notice immediately how much more resistance the broadside orientation creates. That difference is pressure drag in an intuitive form. Air flowing around a blunt shape has to separate and swirl behind the object, leaving a low-pressure wake that effectively sucks backward on whatever created it, while a streamlined shape lets the air rejoin smoothly behind, closing up neatly with much less of that trailing disturbance. This is why airplane fuselages are long and gently tapered rather than boxy, why landing gear gets tucked away into the wing or fuselage once airborne, why engine housings are shaped like teardrops rather than cylinders with flat fronts, and why even small protrusions, antennas, sensor probes, the little vortex generators sometimes visible on a wing's upper surface, are designed with careful attention to their shape rather than just their function. Every blunt edge on an airplane is, in a small way, a decision that trades some drag for some other benefit, and designers are constantly negotiating that trade. Induced drag is the strangest of the three main types because it isn't caused by friction or by an object's blunt shape at all. It is, in a sense, the price of lift itself, an unavoidable tax that comes bundled with the very thing that keeps the airplane up. Remember that a wing generates lift by creating a pressure difference, lower pressure above, higher pressure below. At the wingtip, air doesn't respect that boundary neatly. High-pressure air from underneath the wing curls around the tip toward the low-pressure region above it, because pressure differences want to equalize wherever they can, and a wingtip is simply a place where the two regions are close enough together to touch. This curling motion creates a spinning vortex trailing off each wingtip, visible sometimes as contrails curl into their shape, or briefly visible as condensation in humid air during a hard turn, or dramatically visible in demonstration flights where colored smoke reveals two ghostly, twisting ropes of air spiraling off the tips and stretching backward for what can be a mile or more before finally dissipating. Generating these vortices costs energy that has to come from somewhere, and that somewhere is the engines, showing up as induced drag. The interesting and slightly counterintuitive thing about induced drag is that it gets worse at low speed and better at high speed, the opposite of skin friction and pressure drag, which both increase as speed increases. With low speeds, a wing has to work harder, generating more lift per unit of airflow, which means a stronger pressure difference, which means stronger, more energetic wingtip vortices. This is why induced drag is such a significant factor during takeoff and initial climb, and much less of a factor once an airplane has settled into cruise at higher speed, where the wing doesn't need to strain as hard to produce the lift it needs. This single fact, that induced drag dominates at low speed, while friction and pressure drag dominate at high speed, is responsible for one of the more elegant compromises in the entire history of aircraft design,
because it means there is no single speed that minimizes total drag in every category simultaneously. Total drag, if you were to sketch it as a curve against speed, actually forms a shape like a shallow valley, high on both ends, low somewhere in the middle, and that low point represents the most efficient cruising speed for a given airplane. Engineers spend enormous effort finding that valley and designing an airplane and the routes it flies to sit as close to it as practically possible. Winglets, those small upward or angled extensions you sometimes notice at the very tips of a modern airliner's wings, are one of the more visible responses to the induced drag problem. Richard Whitcomb, an engineer at NASA's Langley Research Center, spent years in the 1970s studying how to reduce the strength of wingtip vortices without simply making the wing longer, since a longer wing brings its own costs in weight and structural complexity and airport gate compatibility. His research showed that a carefully shaped vertical or angled extension at the tip could partially disrupt the vortex formation, effectively acting a bit like a sail, catching some of that escaping high-pressure air and turning a portion of what would have been wasted, swirling energy into a small amount of usable forward thrust. The fuel savings from winglets are real but modest on any single flight, often in the range of a few percent, which sounds unremarkable until you multiply it across a fleet of hundreds of airplanes flying thousands of flights a year, at which point a few percent becomes a genuinely significant quantity of fuel and a genuinely significant reduction in emissions, which is why winglets, once a novelty, became standard enough that their absence on a modern jet now looks almost like an oversight. All of these forms of drag pull designers toward the same broad philosophy, which is to make everything about an airplane's exterior as smooth, as gently tapered, and as free of unnecessary interruption as possible. But that philosophy runs directly into a competing set of needs, because a wing that is perfectly optimized for quiet, efficient cruising at high altitude is often not a wing that behaves well at the low speeds needed for takeoff and landing. A longer, narrower, higher aspect ratio wing reduces induced drag beautifully at cruise, which is why glider pilots, who care about efficiency above almost everything else, fly wings that look almost absurdly long and thin compared to their fuselage. But a wing like that, without help, would demand very high takeoff and landing speeds, requiring longer runways and creating a less forgiving margin for pilots during the most delicate phases of flight. This is why airliner wings carry an entire hidden toolkit of moving surfaces, flaps and slats among them, that only reveal themselves briefly during takeoff and landing, changing the wing's shape temporarily to generate more lift at low speed, accepting extra drag for those few minutes in exchange for a gentler, safer, shorter takeoff and landing, before retracting quietly away again once the airplane no longer needs that help and can return to its leaner, more efficient cruising shape.
So far, we've been talking mostly about lift and drag, as though an airplane were a fixed shape moving through the air in a single, unchanging direction. But of course, that isn't how flying actually works, and it's worth slowing down now to think about how an airplane decides where to go, and how it stays balanced while it gets there. Because staying in the air is only half the problem. The other half is staying upright, staying level when you want to be level, and tilting deliberately when you want to turn, climb, or descend. And none of that happens by accident. It happens because of a quiet, continuous negotiation between the airplane's weight, its shape, and a handful of movable surfaces that pilots and autopilots use to nudge that negotiation in one direction or another. The starting point for understanding any of this is a concept that sounds almost too simple to matter, but turns out to matter enormously, and that is the center of gravity. Every object that has mass, which is to say, every object in the universe, has a single point where its weight can be thought of as concentrated, a kind of balance point. You've felt this yourself if you've ever tried to balance a broom on the palm of your hand. There's one spot along the length of the broom where it balances easily, and if you move your hand even slightly away from that spot, the broom tips and falls. An airplane has a center of gravity in exactly this sense, a single point, usually somewhere near the middle of the wing, where its entire weight can be imagined as acting. And everything about how an airplane is designed to fly and how it's loaded before each flight, with passengers and cargo and fuel distributed carefully rather than dumped in one corner, is built around keeping that center of gravity within a narrow, safe range. The reason the center of gravity matters so much becomes clear when you think about the tail of the airplane, that smaller set of wing-like surfaces sitting far behind the main wings, out at the back of the fuselage. The tail doesn't produce much lift in the way the main wings do. Its job, most of the time, is almost the opposite. It produces a small, steady downward force, pressing the tail of the airplane gently toward the earth. That might sound like a strange thing to want, wasting some of the airplane's hard-won lift by pushing part of itself back down, but the reason becomes obvious once you picture the airplane as a kind of long seesaw, balanced somewhere near its center of gravity, with the wings providing a big upward push near the middle and the tail providing a small downward push near the back. That downward push at the tail is what keeps the nose of the airplane from wanting to pitch upward or downward on its own, the way a canoe tips forward if you sit too far toward the bow. It's a stabilizing force, and it's constantly being fine-tuned, because as fuel burns off during a long flight and the airplane's weight and balance shift slightly, that tail force has to adjust along with it, sometimes by a tiny automatic trim adjustment so subtle that passengers never notice it happening. Sitting at the very back edge of that horizontal tail surface is a hinged panel called the elevator, and this is where things start to become genuinely controllable rather than just quietly stable. When a pilot pulls back on the control column, or nowadays more often moves a smaller side stick, the elevator tilts upward, and this changes the amount of downward force the tail is producing. More downward force at the tail means the nose of the airplane pitches up, tilting the whole airplane's angle relative to the oncoming air, which changes the angle of attack of the main wings, which changes how much lift they produce. Pull back gently, and the nose rises. The wings bite into the air at a steeper angle, and the airplane climbs. Push forward, and the opposite happens. It's worth sitting with that chain of cause and effect for a moment, because it's easy to imagine that pulling back on the controls somehow lifts the airplane directly, the way pulling up on a kite string does. But that isn't what's happening at all. The elevator doesn't lift the airplane. It changes the airplane's attitude, its pitch angle, and that new attitude is what changes the lift being generated by the wings themselves. The climb is a consequence, not a direct action, and that distinction turns out to matter a great deal in situations where an airplane loses too much speed, because pulling back on the controls when the wings are already struggling to produce lift can make the angle of attack too steep, inviting a stall rather than a climb, which is one of the things every student pilot learns to feel in their hands long before they learn to explain it in words. Turning works through a similarly indirect chain of cause and effect, and it begins with a pair of hinged surfaces called ailerons. mounted near the outer tips of each wing, one on the left wing and one on the right, always moving in opposite directions from each other. When a pilot turns the control wheel or tilts the side stick to the right, the aileron on the right wing rises, while the aileron on the left wing lowers. Raising an aileron reduces the lift that section of wing produces, while lowering the opposite aileron increases lift on that side, and the result is that one wing drops and the other rises, tilting the entire airplane sideways into what pilots call a bank. This is worth pausing on because it explains something that puzzles a lot of people the first time they think carefully about it, which is that an airplane doesn't turn primarily by swinging its nose sideways the way a car turns by swinging its wheels. An airplane turns mostly by banking, by tilting itself onto its side just enough that a portion of the lift force, which had been pointing straight up, now points partly to the side as well. Lift is always generated perpendicular to the wings, so when the wings tilt, the direction of that lift force tilts along with them, and that sideways component of lift is what actually pulls the airplane's path around in a curve. This is exactly the same principle a cyclist uses when leaning into a turn, or a skier uses when tilting their edges into a carved corner on a slope. The lean isn't incidental to the turn. The lean is what creates the turn. There's a third control surface involved in turning as well, mounted vertically on the tail, called the rudder, and its job is often misunderstood because people assume the rudder is what makes an airplane turn, the way a rudder on a boat does. In level, coordinated flight, the rudder's real job is subtler than that. It helps counteract a side effect of banking called adverse yaw, in which the very act of raising one aileron and lowering the other creates a small amount of extra drag on the wing that's producing more lift, which can cause the nose of the airplane to yaw or swing sideways, slightly away from the direction of the turn, opposite to what you'd want. A gentle push on the rudder pedal corrects for this, keeping the nose pointed smoothly into the turn rather than skidding sideways through it, the way a car's tires can lose their grip and slide if you don't manage the geometry of a turn correctly. On modern airliners, much of this coordination happens automatically, blended in by onboard computers, so that passengers rarely feel the small correction being made at all, only the smooth, banked arc of the turn itself. There's one more family of surfaces worth understanding before this picture is complete, and these are the spoilers, long panels set into the top of each wing that can be raised to deliberately spoil, as the name suggests, some of the smooth airflow the wing depends on for lift. Raising the spoilers reduces lift and increases drag at the same time, which sounds purely undesirable until you consider situations where a pilot wants exactly that combination, such as during a rapid descent or immediately after touchdown, when spoilers pop up along the wings to kill lift almost instantly, pressing the airplane's weight firmly onto its wheels so the brakes have something solid to grip rather than a machine still half eager to fly. Now let's talk about the air itself, because so far we've been describing wings and controls as though they moved through something calm and uniform, and of course they don't. The air an airplane flies through is restless. It has weather in it. It has currents and eddies and pockets of rising and sinking motion, the same way a river has smooth, glassy stretches and also sudden turbulent boils where the current hits a submerged rock. Understanding how airplanes handle this restlessness is really a matter of understanding two separate questions that often get confused with each other. One is whether moving air can make a flight uncomfortable. The other is whether moving air can make a flight unsafe. These turn out to have very different answers, and untangling them is worth doing slowly. Start with wind itself, the simple sideways or headlong movement of a large body of air. Wind by itself is not something an airplane fights against so much as something it flies within, the way a swimmer doesn't fight a river current so much as get carried along by it while still swimming their own strokes through the water around them. If you're on an airplane, cruising at altitude in a strong tailwind, the plane isn't straining against anything. It's just moving through its local parcel of air, exactly as it would in still air, and that whole parcel happens to be sliding across the ground faster than the plane's engines alone would produce, the way a person walking briskly down the moving walkway at an airport covers ground faster than their own footsteps account for. This is why flight times from, say, New York to London are often noticeably shorter than the return trip. The jet stream, a narrow river of very fast-moving air several miles up, often blows west to east across the Atlantic, and pilots will sometimes deliberately route a flight to ride within it, the same way a rower might steer toward the fastest current in a stream rather than fight the slower water near the bank. Gusts are a different matter, because a gust is a wind that changes, sometimes quickly, and change is what an airplane actually has to respond to, since lift depends on the speed of air moving over the wings rather than on any fixed number on a dial. A sudden gust hitting an airplane from ahead has the odd effect of briefly increasing the airplane's lift, because for a moment the wings are experiencing faster airflow than the plane's own speed through the ground would suggest, the way sticking your hand flat out of a car window feels a firmer push if a gust happens to hit it at the same moment you're already moving forward. This is one reason airplanes sometimes seem to bob or lift slightly on final approach in gusty conditions, and why pilots add a small speed margin, sometimes called a gust factor, to their approach speed on windy days, giving themselves a cushion so that a sudden loss of headwind doesn't leave the wings with less lift than they need at exactly the wrong moment, close to the ground. Turbulence is the broader, bumpier cousin of gusts, and it's probably the single thing about flying that unsettles people the most, which is understandable, because it's the part of flight you feel most directly in your body, jostling your coffee and your stomach in a way that altitude and speed and engine noise mostly don't. But it helps to understand what turbulence actually is happening to. It is not the airplane losing its grip on the sky. It is the airplane passing through parcels of air that are moving up, down, or sideways relative to each other, sometimes because of heat rising unevenly off the ground on a warm day, sometimes because of air flowing over mountains the way water flows over rocks in a stream bed, sometimes because of the jet stream itself, where fast air and slower air rub against each other along an invisible boundary, the way two lanes of traffic moving at different speeds create turbulence for a driver trying to merge between them. Modern airliners are engineered with turbulence loads built into their basic structural design from the start, tested well beyond anything encountered on even the roughest ordinary flight. The wings themselves flexed upward in testing, sometimes visibly, by amounts far greater than passengers ever see in the cabin. The bumps you feel are real, and they can certainly be uncomfortable, even alarming in a strong patch, but they are not, on their own, a structural threat to the airplane. This is precisely why the seatbelt sign exists at all. Its purpose isn't to hold the airplane together. It's to hold you together, keeping you from being tossed against the ceiling or a nearby armrest during an unexpected jolt, which is genuinely the primary way people get hurt during turbulence, not from any risk to the aircraft itself. Clouds deserve a gentler mention here too, because they carry an outsized reputation for danger that mostly comes from limited visibility rather than any physical hazard in the cloud itself. Flying through an ordinary cloud is, for the airplane,
not unlike a car driving through fog. The windshield goes white, the world outside disappears, and instruments take over the job the eyes would otherwise do, which airliners and their crews are equipped and trained for, as a matter of routine, not emergency. The clouds that do concern pilots are a specific and recognizable minority. The tall, boiling cumulonimbus clouds associated with thunderstorms, which contain genuinely violent internal currents, hail, and lightning, and which pilots don't fly through at all, but route carefully around, sometimes deviating a considerable distance off course to keep a wide, comfortable berth, guided by onboard weather radar that paints a picture of where the worst of the churning is happening inside a storm cell, long before the airplane gets anywhere near it. Ice is the other weather-related concern worth explaining calmly, because it sounds ominous and is treated with real seriousness by everyone involved in aviation. But the seriousness comes with a whole toolkit of well-understood countermeasures, rather than helpless exposure to the problem. Ice becomes a concern when an airplane flies through air containing supercooled water droplets, water that remains liquid even below its normal freezing point until it touches something solid, at which point it freezes almost instantly onto that surface, the same way water can sometimes stay liquid in a very clean, very still glass in a freezer until the moment you tap it. If that ice were to build up on a wing's leading edge, it could roughen the smooth surface the wing depends on and interfere with lift, which is exactly why airplanes carry systems to prevent this from becoming a problem in the first place. Some use heated air, drawn from the engines, that's channeled through the leading edges of the wings to keep them warm enough that ice can't form. Others use inflatable rubber boots along the wing's edge that flex and crack any ice that starts to form before it can build up further. On the ground, before departure, airplanes are sprayed with heated de-icing fluid that melts existing ice and, in colder conditions, a second, thicker, anti-icing fluid that clings to the wing and prevents new ice from forming during taxi and takeoff, gradually shearing away as the airplane accelerates down the runway. None of this is improvised in the moment. It's planned for, checked, and in many cases automatic, the way a car's defroster runs quietly in the background on a frosty morning, rather than being something the driver has to think hard about. All of this happens against a backdrop that itself changes with height, because air isn't the same thickness everywhere, and this is where the earlier idea of thin, high-altitude air becomes worth returning to and taking a little further. As an airplane climbs, the air around it grows less dense, molecules spread further apart, meaning there's simply less air for the wings to press against with each foot of forward travel, and less oxygen-rich air for the engines to draw in and burn as well. This is why airliners have to fly measurably faster at cruising altitude than they would need to at low altitude to generate the same amount of lift, the thinner air demanding more speed to compensate for its own sparseness, not unlike how a fan set to the same power will move noticeably less air in a thin, high-altitude atmosphere than it would at sea level, simply because there's less substance there for the blades to catch and push.
It's worth pausing here to look sideways at the whole family of flying things, because up to this point, the story has mostly followed one kind of airplane, and it can start to feel as though there's only one way to solve the problem of staying up. There isn't. There are several, and comparing them side by side makes clearer which parts of the puzzle are truly fundamental and which parts are just one particular solution among many. Start with the glider, because it strips the problem down to its simplest form. A glider has wings, a fuselage, control surfaces, and no engine at all, or at most, a small one it uses briefly and then shuts off. and yet a glider can stay aloft for hours, sometimes covering hundreds of miles, without ever burning fuel in flight. This tends to surprise people the first time they think about it carefully, because the assumption is that an engine is what keeps a plane up, the way pedaling is what keeps a bicycle moving. But the engine's actual job, as covered earlier, is to keep the airplane moving forward through the air, and it's the forward motion through the air that produces lift, not the engine directly. A glider gets its forward motion a different way. It's towed into the sky by a small powered aircraft or hauled up by a winch on a long cable, and once released, it trades altitude for speed the entire time it's flying, gently and continuously sinking through the air even while it appears, from the ground, to be soaring. What keeps it up for so long despite this constant, quiet descent is that pilots seek out columns of rising air, called thermals, warm air rising off sun-heated ground or pavement the same way it rises off a radiator, and by flying in slow circles inside these columns, a glider can climb inside air that is itself climbing faster than the glider is sinking through it. The airplane loses altitude relative to the air around it the whole time, but the air itself is going up, so relative to the ground, the glider gains height. It's a bit like walking down an escalator that's moving up faster than you're walking down. You're still walking downward the entire time, and yet you arrive higher than where you started. This is why a glider can descend safely and predictably, even with no thrust whatsoever, because gliding was never a malfunction to begin with. It was the ordinary, designed-in behavior of every winged aircraft the moment its engines go quiet, airliners included, which is precisely why a large jet that loses all engine power doesn't fall like a dropped stone, but instead continues flying, more steeply and more urgently than it would like, but flying, trading height for speed, exactly as a glider does, all the way down to wherever the pilots manage to put it. Airliners themselves sit at almost the opposite end of the spectrum from gliders, built not to linger gracefully in rising air, but to cross entire oceans as efficiently as possible, at altitudes where the air is thin and cold, and the engines that burn fuel to produce thrust are, structurally, doing exactly what a glider's tow plane does, just continuously, for the length of the entire journey, rather than for a few minutes at the start. Strip an airliner of its jet engines, on paper, and give it a bit of altitude, and it becomes a very large, very heavy glider, one that would descend more steeply than a purpose-built one because of its shape and weight, but a glider nonetheless, obeying the same relationship between forward speed and lift that governs every fixed wing, from a two-seat trainer at a grass airfield to the widest passenger jet built. Propeller aircraft occupy a middle position, closer in spirit to airliners than to gliders, because they do rely on continuous engine power, but differing in how that power gets converted into forward thrust. A jet engine produces thrust by drawing in air, compressing it, mixing it with fuel, burning that mixture, and blasting the hot exhaust out the back at high speed, essentially manufacturing its own fast-moving jet of gas. A propeller, spun by a piston engine or a turboprop, does something that is mechanically simpler to picture, even if the aerodynamics are just as intricate, because each propeller blade is, in effect, a small spinning wing, angled so that as it rotates, it generates something very much like lift, except that lift is oriented forward instead of upward, and that forward-pointing force is thrust, pulling or pushing the aircraft through the air the way a wing pulls itself upward through it. This is why propellers are sometimes described as wings that spin instead of wings that stay still,
a description that isn't a loose metaphor, but a fairly literal account of what a propeller blade's curved cross-section is doing to the air flowing over it, using the same pressure differences and same angle of attack principles as the aircraft's main wings, just arranged to point their useful force sideways rather than up.
Helicopters push this idea further still, because a helicopter's rotor blades are also, in essence, spinning wings, but instead of producing a steady forward thrust while a separate fixed wing handles the lifting, the helicopter's rotor is asked to do both jobs, generating lift directly by spinning fast enough and at a shallow enough angle that the pressure difference across each blade holds the entire aircraft up, with no fixed wing involved at all. This is what allows a helicopter to hover in place, to rise straight up, to hang motionless over a single point on the ground in a way that fixed-wing aircraft simply cannot do, since a fixed wing needs forward motion through the air to generate lift, and a helicopter's spinning rotor can generate that same lift while the fuselage beneath it goes nowhere. The trade-off is complexity and inefficiency at higher speeds, since a helicopter has to fight harder against the air to go fast than an airplane does, which is why helicopters tend to be slower and shorter ranged than fixed-wing aircraft of similar size, excelling instead at the things fixed wings can't manage: hovering, landing in tight spaces, taking off without a runway at all. Birds complicate the picture in an interesting way, because a bird's wing is doing several jobs an airplane splits across separate systems. A soaring bird, riding a thermal exactly as a glider pilot does, is behaving almost identically to a glider, wings held still and outstretched, trading altitude for lift the same way, which is why birds and glider pilots are often found circling the very same columns of rising air, each having discovered the same physical shortcut independently, one through instinct refined over millions of years, the other through careful observation and practice. But a bird that's flapping is doing something no fixed-wing aircraft does at all, twisting and flexing its wings with every stroke so that the downstroke generates both lift and forward thrust simultaneously, the wingtip feathers separating and rotating to act almost like individual small propellers, while the upstroke is drawn in closer to the body to minimize drag. It's a remarkably elegant solution, one that took engineers a very long time to appreciate fully, because early aviation pioneers who tried to build flapping machines, called ornithopters, kept discovering that a bird's flight muscles, bone structure, and feather mechanics are so intricately matched to the task that no simple mechanical imitation could reproduce it, which is part of why the Wright brothers and their contemporaries eventually abandoned flapping wings in favor of the fixed wing and separate propulsion that every airliner still uses today. Paper airplanes, humble as they are, turn out to be honest little demonstrations of the same fixed-wing gliding principle, just at a much smaller and slower scale. A well-folded paper airplane has a wing shape, however crude, and when thrown, it has forward speed, and as that speed decreases and gravity pulls it downward, it too is trading altitude for the forward motion needed to keep air flowing over its wings, gliding in miniature the same way a full-sized glider does, right down to eventually running out of altitude to trade and settling gently, or not so gently, onto the floor. Then there are the odder machines that don't fit neatly into any of these categories, hovercraft that use a cushion of pressurized air to lift themselves slightly off the ground or water without needing wings or rotors at all, relying on air pressure rather than aerodynamic lift in the usual sense, and experimental tilt-rotor aircraft that combine a helicopter's rotors with an airplane's fixed wings, taking off vertically like a helicopter
and then rotating their engines forward to fly efficiently like an airplane once airborne. What ties all of these machines together, despite how different they look and behave, is a small set of shared physical principles expressed differently depending on the shape of the wing, the presence or absence of an engine, and whether that wing holds still or moves. And it's worth sitting with that thought for a moment. This idea that the sky doesn't care very much what kind of machine is asking to be held up in it, only that the machine has found some way, however unusual, to keep enough air moving past enough of a shaped surface, since underneath the metal and the feathers and the folded paper, it's really always the same handful of quiet rules being satisfied in one way or another.
Long before anyone understood why a wing worked, people were already trying to imitate the birds, and the kite was probably the gentlest and most patient of these early experiments, even if nobody thought of it that way at the time. A kite is really just a fixed wing on a leash, held at an angle to the wind so that the same pressure differences we've been talking about push it upward, with the string doing the job that forward motion does for a glider, letting the wind flow past the surface instead of the surface moving through still air. People in China were flying kites more than 2,000 years ago, and while they weren't writing equations about lift, they were, in a very real sense, the first humans to routinely put a shaped surface into moving air and watch it hold itself up against gravity. It's a small thing, a toy really, but it planted a seed that would take a very long time to grow into anything resembling an airplane. The next few centuries offer little in the way of careful experiment, mostly imagination, sketches, and hope. Leonardo da Vinci filled notebooks with drawings of flying machines around the turn of the 16th century, many of them based on flapping wings, ornithopters as they're now called, because birds seemed like the obvious model to copy. He studied bird anatomy closely, dissecting wings, watching how feathers overlapped, trying to understand the mechanics of flight from the only working examples he had access to. None of his flying machines were ever built and tested in his lifetime, and it's just as well, because the flapping approach, as we've already discussed, runs into problems of scale and power that no amount of clever mechanism can fully solve for a human-sized body. But Leonardo's careful observation, even without the right conclusion, was itself a kind of quiet progress, a shift from myth toward something closer to study. The real turn toward understanding came slowly, and much of the credit for that turn belongs to an English baronet named George Cayley, who was born in 1773 and spent much of his long life thinking carefully about what actually keeps something in the air. Cayley did something that seems obvious now, but wasn't obvious then. He separated the problem of lift from the problem of propulsion. Earlier thinkers had mostly assumed that a flying machine needed wings that flapped, because flapping seemed to do both jobs at once, holding the creature up and pushing it forward. Cayley looked at the problem differently, and around 1799, he sketched what many historians consider the first true diagram of a fixed-wing aircraft, with a wing to generate lift, a separate mechanism for propulsion, and control surfaces at the back for steering, essentially the same layout every airliner still uses today. He built gliders to test his ideas, small ones at first, and by 1853, in his 70s by then, he reportedly had his coachman fly briefly across a valley in one of his full-sized gliders, which makes Cayley's coachman, whose name has mostly been lost to history, quite possibly the first adult human to fly in a heavier-than-air machine, however briefly and however roughly he might have landed.
Cayley's insight sat somewhat quietly for a few decades, the way good ideas sometimes do before someone picks them up and runs further with them, and the person who did the running was a German engineer named Otto Lilienthal. Lilienthal took Cayley's fixed-wing concept and turned it into something closer to a practiced skill. Starting in the early 1890s, he built a series of gliders with wings shaped and curved based on his own careful studies of birds, and then he did something almost nobody had done before him with any seriousness. He actually flew them, over and over, jumping from a specially built hill near Berlin, and later from natural hillsides, launching himself into the wind and gliding for measured distances, sometimes hundreds of feet. He kept records. He adjusted his wing shapes based on what worked and what didn't. Over roughly 5 years, he made more than 2,000 glides, which meant he was, in effect, running thousands of small experiments in real air, refining his sense of curvature and control by feel as much as by calculation.
Lilienthal died in 1896 after a glider stalled and crashed, a loss that rippled outward through the small community of people who cared about flight. But his data, his photographs, and his simple, hard-won conviction that fixed wings could carry a person reliably through the air became essential reading for the next generation of experimenters, including 2 bicycle makers in Dayton, Ohio, who kept a well-worn copy of his writings close at hand. Wilbur and Orville Wright approached the problem the way careful mechanics approach any stubborn machine, by refusing to trust anyone's numbers, including their own, until they had checked them directly. They read Lilienthal's work and the published lift tables of the time, tried building gliders based on that information, and found that their machines didn't perform the way the tables predicted. Rather than assume they were building poorly, they suspected the existing data itself might be flawed, which took a certain kind of stubborn confidence for 2 men without engineering degrees working out of a bicycle shop. So in 1901 they built something new, a wooden box about 6 feet long with a fan at one end driven by a small engine, pushing air through the box past small model wings mounted inside, measuring the forces on those tiny wings directly, rather than relying on anyone else's figures. This was one of the first serious wind tunnels, and over the following months the Wright brothers tested somewhere around 200 different wing shapes in it, patiently recording how each one behaved. What they found was that many of the standard published values were significantly off, and their own careful measurements let them design a wing shape, and eventually a full aircraft, based on numbers they had confirmed with their own hands and eyes rather than inherited assumptions. It's worth sitting with that image for a moment. 2 brothers in a shed in Ohio, quietly correcting the scientific record on lift through nothing more than patience and a homemade fan, because it captures something true about how this entire field of understanding has developed, not through single flashes of genius so much as through the slow, repeated checking of ideas against the honest resistance of real air. That wind tunnel idea, simple as it sounds, a fan blowing air over a model while instruments measure the forces involved, turned out to be one of the most important tools in the whole history of flight, and it didn't stop with the Wrights. Through the 20th century, wind tunnels grew larger and faster, some capable of pushing air past full-sized aircraft components at speeds approaching and even exceeding the speed of sound, letting engineers study exactly how a wing would behave before ever risking a pilot's life testing it in open sky. Smoke or colored threads could be introduced into the airflow so that engineers could actually see the air moving, watching it curve smoothly over a well-designed wing or breaking away messily from a poorly shaped one, the invisible finally made visible, at least in part. In more recent decades, a newer tool has joined the wind tunnel without fully replacing it: computational fluid dynamics,
which uses powerful computers to simulate how air will move around a shape by dividing that airflow into an enormous number of tiny regions and calculating, region by region, how pressure, speed, and direction change moment to moment. This lets engineers test thousands of wing variations without building a single physical model, adjusting a curve here or an angle there, and immediately seeing, at least in simulation, how the airflow responds. It's a remarkable extension of everything Cayley, Lilienthal, and the Wrights were groping toward with hillsides and wooden fans. The same fundamental question, what will the air do here, now asked and answered with mathematics running on silicon rather than muscle and canvas. And yet, for all this computational power, actual flight testing with real instruments aboard real aircraft, measuring real pressures and real vibrations in real turbulent sky, has never been fully replaced, because even now, with all our equations and our simulations, the full, chaotic, swirling detail of turbulent airflow remains one of the genuinely unsolved problems of physics, something engineers can predict remarkably well in most ordinary circumstances, but still cannot fully calculate from first principles in every case, which is a strange and rather humbling thing to realize, that we can build machines carrying hundreds of people gently through the sky, while the deepest mathematics underneath that gentleness still keeps a few of its secrets.
So let the mind drift back now, gently, over everything that's been gathered here, the way you might walk once more through a house before turning off the last light. It began, so many sections ago, with something almost absurdly small, individual molecules of nitrogen and oxygen, invisible, weightless seeming, moving in every direction at speeds faster than sound, colliding trillions of times each second in the space above your head right now, in this room, in this quiet dark. Those collisions, that ceaseless jittering motion, is what pressure actually is, not a mysterious force, but simply the accumulated bumping of countless tiny particles against every surface they touch, against your skin, against the walls, against the curved metal skin of a wing cutting through the sky at altitude. Nothing in the story of flight works without that foundation. The air is not empty. It is not nothing. It is an ocean of matter so fine we forget it's there, until a kite pulls against a string, until a hand out a car window tilts and rises on the moving air, until 60 tons of aluminum and fuel and passengers lift smoothly off a runway and does not fall. From those molecules came pressure fields, invisible gradients of push, high pressure here, lower pressure there, and air, always, always moving from the crowded places toward the sparse ones, the way a room full of people might slowly drift toward an open door. A wing, shaped just so, curved more on top than on the bottom, tilted slightly into the oncoming air, persuades the air around it into exactly this kind of imbalance, faster and thinner above, slower and denser below, and the difference between those two pressures becomes, quite simply, lift, not magic, not some special exemption from gravity, just ordinary physics, patiently arranged. And here, memory might return, softly, to that word Bernoulli, and to the gentler correction that came with it, the reminder that the popular explanation involving equal transit time, the idea that air splitting at the front of a wing must rush to rejoin its partner at the back, was a tidy story, but not quite a true one. The real air, above a cambered wing, does not politely wait for its other half. It arrives early, having been accelerated by the wing's curve and by Newton's own contribution to the story. The simple fact that a wing pushes air downward, and the air, in perfect obedience to every action, having an equal and opposite reaction, pushes back upward on the wing. Both explanations, the pressure differences described by Bernoulli's principle and the downward deflection described by Newton's third law, are describing the same real event from two different honest angles, not competing theories, where one must be declared the winner, but two lenses on one phenomenon, each incomplete alone, each true as far as it goes. From there the story climbed into history itself, into Sir George Cayley, sketching the separation of lift and propulsion nearly a century before anyone flew, into Otto Lilienthal, throwing himself off German hillsides again and again, gathering data with his own body before it finally, tragically, failed him, into two bicycle mechanics from Dayton, Ohio, who understood, more clearly than almost anyone before them, that control mattered as much as lift, that a machine which could rise but not be steered was no safer than one that could not rise at all. Their wind tunnel, built from a repurposed fan and a wooden box, tested not one wing shape but hundreds, patiently, methodically, correcting the flawed data that others before them had trusted, until December of 1903, when a fragile wood and fabric craft lifted from the sand at Kitty Hawk for 12 seconds that changed everything that followed. And what followed was refinement upon refinement. Faster engines, stronger metal, wings, shaped with increasing precision, tested first in wind tunnels where smoke and colored thread made the invisible air briefly visible, and later, in the silent calculations of computers, simulating millions of tiny parcels of moving air, region by region, pressure by pressure. But even now, with all of that mathematics, all of that computing power humming away in server rooms, turbulence itself, the swirling, chaotic tumble of air breaking loose from smooth flow, remains only partly tamed by human understanding, predictable in general, resistant in its full detail, one of the genuinely open questions, still sitting quietly at the heart of physics. Which brings the story, at last, to the parts of flight closest to ordinary experience, the parts a passenger actually feels. Takeoff, when an engine's thrust finally overcomes the drag holding a plane back, when speed builds down a runway until the wings are moving through air fast enough to generate more lift than the aircraft weighs, and the wheels simply stop being needed, the ground falling away, not through any dramatic leap, but through a threshold quietly crossed. Balance, the constant, invisible negotiation between four forces, lift working against weight, thrust working against drag, a negotiation that never fully stops, adjusting itself thousands of times a minute, through both the pilot's hands and, in most modern aircraft, through computers responding faster than any hand could. Control, achieved not by brute force but by small persuasions, ailerons tilting to roll the plane gently left or right, a rudder nudging the nose, an elevator raising or lowering the tail, to pitch the whole aircraft up or down, each surface working by doing exactly what a wing does, changing the air's behavior just enough to shift the balance of pressure and let the aircraft lean into a new path through the sky. And turbulence, that word so often spoken with a flicker of unease, deserves one last gentle reframing before rest. It is not the plane struggling against the sky. It is simply air behaving the way air behaves when it meets uneven heating from the ground below, or a mountain range disturbing its smooth flow, or the invisible boundary where two different wind currents brush against each other at different speeds, the same kind of disturbance that ripples a flag or stirs dust on a road, just larger,
just higher, just less visible from where you sit. A modern airliner's wings are built with a flexibility that would surprise most passengers, designed to bend, sometimes visibly, absorbing these bumps the way a long fishing rod absorbs the tug of something pulling against it, rather than snapping rigidly against a force it was never meant to resist without yielding. And gliding, that quiet coda to the whole story, the reminder that even without engines at all, a wing does not simply drop. It trades altitude for forward motion, the same lift and drag relationship at work, just without thrust replenishing what drag steadily removes, the aircraft settling gradually downward while still moving forward, the way a paper airplane released from a hand does not fall so much as descend, unhurried, following a shallow path shaped entirely by the same curved surfaces and tilted angles that carried it up in the first place. Gravity is never defeated in any of this. It is only, briefly, patiently, outmaneuvered. Somewhere in all of this, the careful distinctions matter too. The difference between what is precisely, rigorously true, the equations, the measured pressures, the forces balanced in Newton's own language, and what is merely a helpful simplification offered to make an enormous idea fit inside an ordinary conversation. Both have their place. The simplified story lets a curious mind take its first steps. The fuller story, with its acknowledged edges and its honestly unresolved corners, is what real engineers still work with, still refine, still occasionally get quietly humbled by. And now, if you're still here, still listening, let all of that settle rather than sharpen. There is no test waiting, no need to hold the difference between Bernoulli and Newton in any tight grip. Let it go loose in your mind, the way a wing releases the air behind it, unclenched, unhurried. Notice, instead, the air around you right now. It is doing what it always does, moving almost imperceptibly through the room, carrying warmth away from your skin, settling gently against the covers, holding no urgency at all. It doesn't need managing tonight. It doesn't need to lift anything. It's simply here, patient flight, doing what air has always done.
Let your breathing slow into that same unhurried rhythm. Let your shoulders soften into whatever is holding you. There is nothing left to explain, nothing left to follow, only the quiet dark, and the air moving softly around you, asking nothing at all. Rest well.